Okay. So yeah, going back to this problem, we were interested in the falling mass, right? And I started with Newton's second law for this falling mass. And I'm studying things linearly because the mass is falling down, it's not rotating, right? I drew the forces acting on this mass. Now, in the exam, you're expected to know how to make this figure. This figure, you should know how to make it in the exam. Namely, you can see we have a falling object, so we have a tension and a weight. Anything that is downward, I put it to be negative. So I put minus W plus the tension force. This is equal to minus MA. Why did I put the minus sign here? Because it's accelerating downward. So A is downward as well. Okay, I'm trying to find the acceleration, right? If I rearrange for the acceleration, I'll have minus W plus T over minus M, right? I have the mass, so I can find this, but I don't have the tension. And this forces me to study either another direction for Newton's law, because I took the vertical direction here, or another object in my system. Now, can I here study Newton's second law in the horizontal direction? Is it useful to study the horizontal direction for the falling mass? No, because I don't have any forces that are horizontal anyway. Now, if you look at the disk, which is our second object in this system, I can check the forces acting on the disk. Namely, I have the weight, and I have the tension, and I have the normal. This is the same as the previous problem, right? So I have a normal force here, and a weight, and a tension. Now, for the disk, I will prefer to study the rotational form of Newton's law. I will not write, so this is our disk of mass capital M. I will not use F equals MA. Why? Can I use F equals MA for the disk? I can, right? But I will not. Why? Can I use Newton's second law, which is F equals MA for the disk? Even if it's rotating, I can still study the linear quantity. But the thing is, if I use F equals MA, another unknown will emerge, which is what? There's a force which I don't know, and it's really hard to find. It's the normal force. Okay, so if I try to use F equals MA, I don't know the normal. I already don't know the tension, so it's gonna be hard. Whenever you have anything rotating, it's always easier to take the rotational kinematics and dynamics. So I'm gonna use the rotational form of Newton's law here, which is tau equals to I alpha for the disk. You all agree? What am I gonna write here? T times the radius times sine 90 equals, so as before, the weight and the normal don't contribute to the torque, only the tension force will contribute to the torque, right? And here I'll have half m r squared. I'll put capital M because I'm studying the disk versus the falling mass. The falling mass has small m, the disk has capital M. And I have alpha. Now, here, I got my second equation, this one, and this is my first equation. What do I want to find in this problem? I want to find the acceleration of the falling block. So this is what I want. In my second equation, I can find the tension, but it will be in terms of what? Alpha, right? I need to find alpha, or even better, I can write alpha in terms of the tangential acceleration, which I want to find anyway, right? Isn't alpha equal to A over R? And which A is this? It has to be the tangential, not centripetal, right? A tangential, which is none other but the acceleration here. This is A tangential. The disk has two acceleration components, a tangential component and a centripetal component. The centripetal one tilts the velocity. The tangential one changes the velocity, right? And this tangential acceleration is the same as the acceleration of the falling mass. Otherwise, if they are different, the rope will snap, right? So this is also AT. A of the small mass is equal to A tangential of the big mass. All right? So this is going to be A over R, where A is the acceleration of the small mass. I will plug this here. I'll have half m r squared am over r. And here this reduces to tr. I'm going to try to find the tension, plug it up here to deduce the acceleration. Makes sense? So I'm solving two equations, two unknowns, essentially. You can see that r and r here cancel out, and r here also cancels out. I got half m A of the small mass. This is our tension. So A of the small mass will be equal to minus G plus half m am over minus m. Did you see what I did here? This is the acceleration formula. I substituted W by mg, and m canceled out. I got minus g. Actually, it should be plus g, right? Yes. And here the tension, I substituted it with the expression I got here, which is half m am. And here I have the falling mass in the denominator. It will not cancel out. I'm going to take am to the other side, right? So I'll have am plus 1 over 2 m over m am equals g. Does this make sense? Now I'll take am to be a common. I'll have 1 plus half m over m equals g. So I'll get am equals g over 1 plus m over 2m. We got the acceleration of the falling mass. Any questions? So the weight W, look at my first formula here. So I have a question, how did we get this plus g term here? W is equal to mg, do you agree? Yeah, so this is equal to minus mg plus t over minus m, which I can write as minus mg over minus m plus t over minus m. These cancel out, يبقى g plus t over minus m. All right? Yeah. We find the acceleration. Part B, we want the angular acceleration of the disk. That is so easy. Knowing our acceleration, how can I find alpha? Yeah, I have
Alpha.
this formula.
Okay.
Exactly. Alpha is A of the mass over the radius. I have the radius. You can easily find the angular acceleration. And we want the tension in the cord. I'll just use this formula to find the tension. I found the acceleration. I can deduce the tension, right? So I have the final answers here. The acceleration, this is the formula we got to. And if you calculate, you get this answer. The tension is minus half ma. So you substitute the acceleration you got to deduce the tension and the angular acceleration. Makes sense? Any questions? Questions? Okay. This is an easy question, but let's take a look at it. Find the rotational inertia of a wheel that has a kinetic energy of 24,400 joules when rotating at 602 revolutions per minute. Okay, what's my formula for kinetic energy? Yeah, it's half I alpha squared. We want the rotational kinetic energy. So what we have is the rotational one, K is equal to half I omega squared. I'm given this is 24.4 times 10 power 3 joules. What we want is this. Do I have omega? This is the angular speed. Do I have it? Yeah, so this quantity here is actually omega because I can tell from the unit, revolution per minute or angle per minute, right? However, what's wrong with this omega? Exactly, it's not SI, very easy. I'm gonna be just converting it and the rest is just calculation. So I is gonna be 2K over omega squared. I'll put 2 times 24.4 times 10 power 3, and then I'll divide by omega. How do we convert from revolution per minute to, what's my SI unit? Radian per second. I have two conversions to worry about, revolution to radian and minute to second, okay? Yeah. So I'll write revolution to radian. How do we convert? Multiply by 2 pi, excellent. Minute to second, I'll multiply by 60. However, this is in the denominator. So if I want to do this to the value, which is 602, I'll multiply by 2 pi, because this is in the numerator, it's fine. But then I'll divide by 60, because this is in the denominator.
Professor,
Yes.
إذا كانت revolutions per second to radians per second كيف بنحولها ولا ما بتزبط؟
So I'll write them down for you as a note.
Please.
These are not given in the exam. So just be aware of that. Revolution per second to radian per second times 2 pi. Revolution per minute to radian per second times 2 pi over 60. Makes sense? All right. Questions on this? Any questions? All right. I'll move on to chapter 11. Or maybe should we do the quiz right away? شو اللي Wednesday? لا, we should do it today. And I'll do another one on Wednesdays. It's okay. Okay, please go ahead, work on the quiz, and we'll stop here.